Good morning, everyone. Welcome to our first webinar of 2017. Today we are presenting integrated motion and finite element analysis with SimWise4D. SimWise4D is a product from Design Simulation Technologies, who we partner with as a reseller for North America. We're going to go through a certain number of things today. First, we're going to introduce ourselves, introduce Design Simulation Technologies. I have a colleague of mine from DST on the line who's going to take over fairly shortly. So we're going to introduce SimWise, both definitions, what it does, what it can do, what it cannot do, and what you should be using it for, as far as benefits of using this product and simulation in general. And we're going to go through a product demonstration. So Scott is going to take us through a standard, I guess, day in the life of a SimWise user, getting data from a CAD system, and this time would be CATIA, and applying motion and function to drive a mechanism and calculating finite element stresses and fatigue and a lot of things. So once that's done, we'll go back and open up for Q&A. So as far as who we are, Tentec LLC, we are a certified women-owned small business. We are ITAR registered. We participate in a lot of government activities, mostly defense, aerospace and defense. We have two offices, one in Los Angeles and one in Billerica, Massachusetts. And we provide services, engineering services, but also provide software and education services. So we are members of a certain number of activities through AIAA, for instance, or VITA. So taking part in consortiums or discussions on aerospace, on finite element analysis, and so on and so forth. So as far as myself, so I'm one of the co-founders of the company. I come from the aerospace world, about 25 years in the industry, both in Europe, started in Europe and migrated to the US a few years ago, quite a few years ago actually. Worked at different engineering levels, naturally at the bottom of the list as a young engineer, all the way up to managing a team of engineers in an office. And worked in mostly in the CAE world, so finite element, dynamics, thermal, across different programs, including GSF or Marsh Rover. And at this point, I manage the analysis team in your company, and also enjoy doing project management and managing technical aspects of the company. Here are some of the projects, or I guess some examples of projects across different industries that we worked on. So on the left, for instance, you have the Link NYC, which is it's a display and wireless repeater and bridge that is deployed across New York City to provide the free Wi-Fi and other capabilities to the public in New York City. So we started helping with the design and the conceptual design. We actually helped qualify the product, going through reviews with the City of New York, and we helped them refine the design and make sure that everything was working accordingly. Similarly, towards the middle, we have a lot of experience with military applications, both thermal and vibration and motion. And towards the right, something a little bit more, I guess, exotic is a giant telescope that is installed in Chile, for which we actually looked at a certain number of things for qualification, including vibration, motion, even aerodynamics of the telescope, given high winds, loads, and things of that nature. The company designing this product wanted to make sure the optics were going to survive all the harsh environments, and the telescope was actually able to point the optics in the right location, and you can imagine the accuracy required for something that's pointing at the sky at deep space. So those are some of the examples of things that we do for a living. And another part of our company is software solutions. We are a partner across North America with Design Simulation Technologies, reselling the line of products that Design Simulation Technologies provides, being working model to the SimWise4D and Dynamic Designer. Today we're going to focus on SimWise4D, and we'll have Scott from DST present the product for you. Scott, I'm going to pass it to you.
Okay, thank you, William, and hello everyone. My name is Scott Ziemba. I'm Director of Technical Services with Design Simulation Technologies. We're here in a joint effort today with Tentech LLC and taking a closer look at the product they now resell called SimWise4D. SimWise4D is a multi-simulation environment that's powerful yet easy to use and allows you to understand different analyses such as 3D motion simulation, linear stress and deflection analysis, durability, as well as optimization. We have a short presentation we'll walk through first, and then we'll move on to a product demonstration. SimWise is comprised of three main products. First is the SimWise Motion that allows you to do rigid body kinematics and dynamics of CAD assemblies. Next, there's SimWise FEA, which is linear static stress and deflection for parts and assemblies. And we can also do things such as transient and static thermal analysis, natural frequency, and buckling. And then there's the SimWise4D, which is a blend of both the motion and the FEA combined into one environment, and the 4D stands for FEA, in case you're curious. And the real benefit of combining those two together is that SimWise4D allows for the simultaneous solution of a motion and FEA with every frame of the motion simulation. Finally, we have an add-on module to the 4D, which is SimWise Durability, which allows you to calculate the fatigue life of your products. SimWise can function in two different ways. The first is as a bidirectional associative plugin with the CAD system shown there on the screen. And when it functions in this nature, it automatically transfers the colors of the parts, the mass properties, the inertia properties, as well as the assembly constraint relationships, and it automatically converts those relationships into corresponding SimWise constraints. The advantage there is that any change done to the CAD model can be automatically updated in the SimWise environment. So there's a bidirectionality between those two programs throughout the simulation process. The other way it can be used as a simple file open type access to different neutral type file formats, as well as NX files, Pro Engineer, and CATIA. And finally, SimWise has some extensive output capability for taking the model up to some different programs for further analysis, for more advanced simulation, integration with control systems, and things of that nature. SimWise has a wide array of motion constraints that are available, allowing you to create kinematic type relationships and motors and actuators, different transmission type constraints, as well as general type flexible connectors and generic constraints. So however the model might need to be represented in the physical world, SimWise has quite an array of different constraints to support that. Different input capabilities in SimWise are allowed to be controlled through what we call the function builder, which is very comprehensive in its capability. So in the function builder, we have the ability to create different mathematical representations of the inputs, whether it's a force or an actuator speed. And we have this graph preview that you can see there that allows you to see what that input's going to look like before you apply it to the feature. There's a set of predefined curves that can be used. There's also the ability to input spreadsheet data to drive your model, and this is a great way to correlate the model with physical test data. So you can drive that model using that real-world test data that was captured. So this could, for example, be velocity data for a motor. It could also be force transducer data that you're applying to some loads in the model. And then finally, SimWise offers the interactive controls where you can create these slider controls and change the speed, for example, of a motor in real time while the model is simulating. Some of the output capabilities, typical things that you'd acquire from physics calculations, displacements, velocities, accelerations. You have the ability to view this in graphical form as well as numerical form, and you can also find the min and max, which is a real benefit too. Create trajectory paths to see visually the profile that something might be moving through during the simulation. And you can also export meter data to Excel for different processing. SimWise offers keyframed animation and photorealistic rendering. So once the model in simulation is created, now you have a great way to create a nice design review or a sales presentation of this model's animation. Some of the visual aids that it offers: the Constraint Navigator, which allows you to cycle through the topology of the mechanism, and we'll demonstrate many of these features that we're talking about, by the way. The Kinematic View, which gives sort of a free body diagram representation to verify that you have your model connected properly. And then Display Vectors, one of my personal favorites, that allows you to show these vectors, such as these blue force vectors on this grapple, that give you a static snapshot in time or during the entire range of motion of the directions and the magnitude of the forces that are occurring. So it's a great way to visually see what's happening to the model as you also place meters on the screen and have those numerical values to look against. And then we have annotations and callouts, like you see in that same grapple there. We have an annotation flag here where this value is updating in real time. So as the force and the actuator changes, the force flag on this call out right here will also change. And then dimensions are dynamic. So as these grapple arms open, the dimension will change in real time, showing the distance as it cycles. SimWise is really an FEA tool for designers or design engineers. So it's nice that it's easy to set up and apply boundary conditions and mesh your model, and it has convergence tools called H-adaptive analysis for helping you converge on a good mesh and result set for your part. So the intent is not to be real complex and get lost in it. It's meant to be a good basic tool for understanding stress and deflection, linear static stress and deflection, that is, of parts and assemblies. And the H-adaptive tool in here allows you to automatically refine the mesh in those high stress gradient areas. So it can be used as a hands-off approach to meshing or a hands-on. So with the hands-off, you can use the H-adaptive method, and with the hands-on, you still have access to things such as the mesh size, if you want to specify the mesh size of different parts and features, and also mesh control to specify the mesh on a fillet or a whole edge or something like that. If you're not familiar with what H-adaptive refinement is, it allows the software to automatically refine the mesh in areas of a high stress gradients only. And that's a very efficient way of meshing, because the solver and the mesher will only focus on refining the mesh in the areas of high stress gradient error. And so then it spends less time trying to pack a nice tight mesh into areas that don't necessarily need it, which is a common misuse of FEA today. People think that the smaller the mesh, the better the results must be. Well, you get to a point where there's efficiency also, and so the smaller you make the mesh, the longer it takes to run the analysis, because now the more nodes and elements you've introduced. Having H-adaptive analysis allows the software to determine where that mesh needs to be refined. Some of the FEA capabilities, as we mentioned, the automatic mesh generation. There's also the linear static stress and deflection, natural frequency, buckling, and steady state thermal, transient thermal, as well as thermal structural. So a great way to look at the stresses in the part while it might be subjected to sub-zero temperatures, for example. And then finally, we talked about that real benefit with SimWise4D is the ability to do a quasi-static analysis of calculating the stress and deflection of a part and seeing the stress and deflection while the motion simulation is occurring. Why the 4D? Why SimWise4D and we'll have that combined motion and stress analysis together? Because stresses resulting from dynamic motion situations can be very difficult to calculate by hand if you've ever tried that. Peak load does not always equal peak stress. Just because something is in a maximum state of bending doesn't necessarily mean that it's not also in a high state of shear. Or vice versa. So you might need to look at the stresses through the entire range of motion to find that most extreme condition. And automatically assigning those boundary conditions really helps the user prevent making the mistake of misapplying the wrong value, the wrong direction, and importantly, the wrong type of load as well. The SimWise durability add-on, or the durability module, excuse me, is an add-on to the SimWise4D product, and it allows you to calculate the fatigue life of your parts. SimWise can also co-simulate with Simulink, for example, so you can integrate control systems in conjunction with your motion simulation to get that realistic input and output feedback in a real-time fashion as your SimWise model is simulating. And also on that same note, SimWise will work with SimScape Multibody to co-simulate, similar to co-simulation, except the motion solver is part of Simulink. So we have a tool that will read the geometry into SimScape Multibody so that you can create advanced analyses using SimScape Multibody control systems. And then finally we have the optimization engine inside of SimWise4D. This comes standard. It's not an add-on module. And it uses HEEDS from Red Cedar Technology. Red Cedar is known worldwide for their optimization software and techniques. SimWise has an interface that's using the HEEDS engine, and it's really a very nice tool that allows you to take that design and simulation and optimize it for many different criteria or many different objectives. So it's a pretty simple process, but yet very powerful in what it does. You simply define what variables you'd like to modify in the design or what are going to be changing, and you specify the boundaries of those variables. And then you specify what your objective is. Perhaps it's to minimize the mass of a part that's going to be produced in high volume production. And yet you're trying to stay within a certain set of constraints. So maybe you're trying to minimize the mass of that part, yet achieve a factor of safety less than 1.5. Or excuse me, greater than 1.5. So with that said, we're going to go ahead and move on to the demonstration. So we'll go ahead and we'll toggle over to SimWise. I have the SimWise environment opened up right here, and let's take a quick look at the environment. So when I'm going through the demonstration, you've got an idea of some of the terminology I'm using. Up here we have our toolbars that give us access to different things such as chords and constraints. We also have some primitive shapes that we can create in SimWise. On that note, I'll just do something very simple here. If we just create a beam, apply a fixed restraint, and solve an FEA, we've got a basic beam and bending, but you can see how quick we got results for that. Okay. Over here we've got the browser. As we begin to bring in CAD models and build the model, we'll see more features get added into this. It shows us basically the hierarchy of our entire model. Down in the middle we have the connections list. This is particularly nice because if we click on any feature in the model, such as this restraint back here, it'll show us anything that is associated or linked to that restraint. For example, there's a cord linked to that restraint, and that restraint is also tied to body 1 right here. So it's a nice way to help sort of understand the structure as we're going through and building the model. Finally, down here we have what's called the properties list. If we click on any body, for example, and open its properties, we have what we call the properties dialog for that body or feature or whatever it might be we're clicking on. Down here in the properties list, there are checkboxes for several different types of things that we can turn on. If these checkboxes correspond to the tabs that are shown in the properties dialog. So for example, if we wanted to turn on vectors, we could click this option next to vectors, and it allows us to turn on a Vectors tab in this Properties dialog. Okay, so with that said, we're going to go ahead and we're going to get started. We're going to, in this example, take a look at reading in CATIA geometry. So I'm going to go ahead and choose File, Open, and I've got a A380 landing gear model here. Go and look at our CATIA. So you'll notice here in the list too, there's all those different formats that we support through direct read in SimWise. So lots of different files that we can open up directly. And then we have this A380 assembly. I'm going to go ahead and double click that. This takes about a minute to read in, but I think it's good that you see it in real time. It shows you the true time it would take to read in something like this. And this is going to bring in all the geometry, also the colors. And there is a checkbox option that we have that I didn't show there before I opened this file, that we can bring in the material properties from the CAD system if we wish to read those over into SimWise. It is easy enough once it's in SimWise to also define our own material properties here. Okay, so it's getting ready to redraw the model. And there we have the full landing gear assembly. Okay. So we're not going to simulate this entire assembly. I simply wanted to show you how quickly we could read in a complex assembly like this into SimWise. What we're going to do is we're going to do a subsystem of this, or a subset, and we're going to look at the landing gear mechanism only, and we're going to look at a few different characteristics of that. But let's first do this. Let's close this model, and we'll close that one. And I want to open up that full landing gear assembly that we have completed already, so you can see what it looks like after we've applied all the constraints and inputs to it. And as an experienced user, this took probably about an hour and a half to build. Okay, and you can see we have some meters that are shown with it. And there we have the full assembly. And so to play this back, I can click on this little playback slider right here, and I can drag this. And I can move this. I'm trying to do it slow enough where it's not real jittery from a graphics perspective. Okay, so we've got a full cycle there. And the full cycle is defined over an interval of about 19 seconds. I'm not an aerospace person. I don't know if those are exact timings or inputs, but simply for demonstration purposes. We can also click on the play button, and that'll play it back smoothly. And we can change the fast forward increment, and we can save this to a video file as well. So as I mentioned before in the presentation slides, it's great for design review, sales presentation, that kind of thing. Okay, so I'm going to go ahead and stop it, and I'm going to close that. And as I mentioned before, we're going to look at the landing gear only. So what I've done is I've had created a model that's only that. So I call it the gear only start. So we'll start this model. And in the interest of time, I'm not going to define all the constraints in here. You can see that I've gone through already and defined the kinematic constraints for this mechanism, but I have purposely left out a few of them. Let's take a look at what happens if we just run the simulation button, let it fall with gravity. Okay, obviously that's not how we want our landing gear to function, but we can see that we are missing a couple restraints on some parts there. Okay, so let's go ahead and start taking care of that. Now before I do that, there's a few housekeeping things I'd like to do. One of those is let's set the units. So we can right click here and we can go into the main display settings, and this also brings up all the simulation settings, and we'll specify that the units are going to be SI units. Notice that we have several different sort of unit packs, if you will, that we could choose from. So we can choose from several different types of predefined unit sets, or we can customize our units. I'll start with SI degrees, but then I also want to change the distance unit over to millimeters, and then I'll change pressure to megapascals because we'll be dealing with some higher stress values, so that's a better value for that. The next thing we'll do is we'll define all of our materials in here to be titanium. I mentioned I'm not a aerospace guy, but for the demonstration purposes, I do know that most aircraft parts are made out of aluminum and titanium. So just to show this feature in SimWise, I'll go ahead and I'll select all of these bodies. I'm not interested in the wheels right now. We'll take care of those in just a minute. We're going to do something else with those. So we have all these bodies highlighted. We can simply right click, choose properties, and then we can click on the material tab, and we can change, and we can customize our materials. Notice that we can edit the database and we can add our own materials into this database if we wish. But I'm going to go ahead and I'm going to choose titanium off of the list. So now we have titanium for everything. I do not see a mass value in here because I've done a multi-select. If in fact I went and did an individual pick and then clicked on that, I would see the individual mass value for that. The next thing we can do is go ahead and begin by creating a subassembly of this wheel structure here. So what we can do is attach the wheels and the hubs to the axle. So for this simulation, we're not necessarily interested in any dynamics of the tires or anything like that. We're strictly interested in some of the kinematics and the inputs to this landing gear mechanism up here. So to simplify this, what we can do is we can create a subassembly, and I'll just go ahead and I'll select those wheels and hubs, hold down the control key so I can do another intermittent selection here, and now I've got those all selected. Hold down the control key again and I'll pick that axle part. Okay, and then I'll go ahead and I'll insert a subassembly, and I'll call it the axle. Whoop, the axer. All right, so let's rename that properly. Okay, and if I look under that axle now, I can see all of those parts grouped under there. Now there's a couple things I can do. One is I can right click on this subassembly top level and I can choose rigidly joined bodies. That will create fixed joints between all the different parts in the subassembly. Maybe later on I want to go and dismantle that subassembly for some reason. Another way I can use this is I can replace everything with a single body. I'm going to go ahead and do that because that's going to improve the efficiency of my motion calculations, because those are less equations that I'll have in the solver. And like I said, I'm not interested in any of this down here. I'm only interested in the mass of those components. So let's change the transparency of those so they're not so dark. There we go. And now let's double click that. And it's one complete body now, but the mass is tremendous because these tires are solid bodies. They're not, the program doesn't know that they're hollow. But we'll go ahead and we'll override the mass and we'll enter something a little more reasonable, like 650 kilograms for that entire assembly. Okay, so just to see where we're at, I like to run the simulation now and again to see how things are connected, if things are falling apart. And of course, the wheels are connected, but that bracket is still not connected. And I did that on purpose because I wanted to show you how we would go about adding some constraints in SimWise. So there's several different ways to add constraints in SimWise, and one of the ways I'm going to show you is by first using chords. Chords is this tool right here, and what chords are is they are miniature coordinate systems, and they have both location and orientation. And they are the basis for all the features in SimWise, such as constraints and forces and springs and whatnot. Each constraint has two chords, and there is a chord attached to each body that the constraint is joining together. So I can click on this chord tool, and it will filter out all the circular edges and arcs in the model, and then I'll hover my mouse over that circular edge, and you can see the crosshair changes to sort of a bullseye. That means I've grabbed a circular edge, and I'll click, and it just created a chord, and you can see that chord, and it has an XYZ orientation to it. And so this chord is useful because I can also obtain information when it comes to creating meters, and I can use that chord as its own respective coordinate system or reference frame. I'll go ahead and I'll create another chord on that circular edge, And that's all I need. I don't need one here at the middle of this constraint location because there's already one associated with this link that's in the proper position. Now the next thing we do is that cord is attached to this link right here. We can right click on it and choose Create Constraint. Again, this is only one way of creating constraints in SimWise. And it shows us that we've just selected cord 8 on link A, and it's going to create a new cord on the background to finish this constraint. And I'm going to go ahead and choose spherical joint and choose create. You might wonder why I created a spherical joint here. Whenever we deal with any type of rigid body motion simulation product, we have the potential for things called redundant constraints. And redundant constraints have implications when it comes to calculating forces. And so we try to build the model and assemble it with what we call these primitive constraints such that there are no redundancies in the model. We have another cord back here, and if I click on this link right here, down in the connections list, again I can see everything that's associated with that link. And I see I have that first constraint I just created, and then I have these two cords here. And if I hover my mouse over these cords, move it back and forth, you'll see over in the graphics area those cords and constraints and things are highlighting. So I'm going to right click on cord 12 and then choose Create Constraint. Just like we did for this constraint, we're going to go ahead and use that cord on that body, have it create a new cord on the background in that same place, and we'll join those two cords using, this time, a spherical joint on slot. So essentially, with this spherical and this spherical on slot, we have a single degree of freedom pivot right here along this axis. Finally, we have a constraint right here between these two members, and this time I'll click on this link and hover my mouse, and there is the cord 312. I'll click on that cord. This time I'll hold the control key and I'll pick this other link. So this time I've clicked a cord and a body. And now I can right click and choose Create Constraint, and it recognizes that I'm grabbing a cord on one part, a body on another, and I'll go ahead and I'll join these two with a spherical joint. And you'll notice before I leave here, when you bring parts into SimWise, you'll have several different options for joining those parts together and assembling them, just like you would in a CAD program. So SimWise has the same type of assembly sort of joining, if you will. We'll go ahead and create, and now we have that constraint there. Okay, so now to verify our constraints, what we'll do is we'll use the Constraint Navigator. If we right click on any constraint or any body, any feature in SimWise, we can use the Constraint Navigator, and that allows us to cycle through the connectivity of the model. So we can verify that we have things properly connected. So we could also click on this single constraint, for example. Maybe we'll choose this one, and it shows me over in the connections list I've selected constraint 310, and it's connecting this link C and link B right here, and it's made up of these two cords. If I wanted to move that constraint, I would simply move the positions of these cords right here together, and I can do that as a group effort simultaneously. Very easy to do. Okay, now you might notice this link right here is a little more primitive looking than this one. I've purposely done that. I've created sort of a rough blank of this link because our objective is to take a look at some of the stresses in it and say, okay, let's we verified that this link is not exceeding any of the stresses beyond yield, so let's bring in something that's a little lighter weight and yet make sure that we still don't exceed those stresses. So we're using this sort of as a first pass in our design. And again, I've done that on purpose, and I want to show you how we can swap this part out with a new part once we've determined what the final link might look like. The next thing we're going to do is take a run at the simulation here, and we'll go ahead and click the Run button. And just make sure that that looks a lot better. That link is not flopping around. Certainly not how we want the final landing gear to look. Okay, not even the simulation is happy. It's returning some error messages on us, but I don't blame it. Okay, so we'll stop that and rewind it. Next, we'll go ahead and we'll define some inputs to our actuators. Now, there are different types of inputs that you can bring in. If I click on this, I've called it the upper control arm actuator, so I just call it upper control arm here. If I click on that, you can see I have these actuators that are predefined. So I've already gone through. Let me change the transparency of these so you can see it. And I don't think I got that one there. Okay, you can see that actuator inside, that green icon. So I've got an actuator in there, and I simply am using just a force actuator of 0 right now. But what I'd like to do is I'd like to drive these 3 actuators. I have this one here, and I've got this main strut as well that the controls or hydraulics have the ability to control the positioning of that as well. But what I'm going to do is read in data that I have from a spreadsheet. So let's pretend that we have some physical drive data that was gathered, and we know what these actuator displacements need to look like. So I'll double click this actuator, this one here for this upper control arm, to open up its properties. And I'll click on the length displacement option. And here I've got this little triple dot button. As we saw in the PowerPoint presentation, this will access the formula builder. So this gives us access to a wide array of inputs to defining, whether this is an actuator, a motor, a spring. We have the ability to define different types of functions or curves and that kind of thing. If I look under the function tab, I've got predefined curves I can choose from. I've got logic statements that I can use, and I've got math functions. And I can create some sort of a criteria. So perhaps I want this actuator to only cycle at a certain time and then stop completely. And here's where we would define an input slider control. Maybe we want to put a slider up on the screen to control the displacement. We also talked about that in the presentation. So let's go ahead and let's choose the data table here. And I've got some data stored. Let's go ahead and let's open that up. And that's not the data that I wanted. I think we're in here, input data. Here's the upper control arm. What this is displacement versus time. So I've got about 9 seconds of data in here, and the entire displacement cycle that will extend it downward and retract it back up. I don't know how realistic this time is. It may be approximate. As I mentioned, I'm not an aerospace guy, but I think it covers the demonstration just fine. So there's where that's what our input looks like there. And we can also stretch this out, get a better look at it. We can even manipulate this curve and drag these points around if we wanted to. And we can save them to a spreadsheet. If we define our own curve in here, we can store that. Okay, so let's quickly go through and we'll do the remaining actuators. We have the main strut. We'll change that to a length displacement. Read in the data table. There's our main strut profile. And then finally we have the lower control arm. And we'll read that in. So now we've got those 3 inputs defined. Now, as I mentioned, we have 9 seconds overall of displacement data. So let's go ahead and let's specify how long we want the duration of the simulation to be. We can set what's called a stop control. If I go into the main simulation settings here, or a run control, we can stop the simulation when time has reached 9 seconds. Again, here's that triple dot button right here. This brings up that function builder. So if there's some other criteria we'd like the simulation to stop at, we can specify it here. For example, we could say that we want the simulation to stop once the force in a particular joint exceeds a certain value. Okay, so after 9 seconds, and let's go ahead and we'll run the simulation. We'll click the run button. After the simulation is done, probably what I could have done before I ran it is create a couple meters. So we can create meters for just about anything in here. Chord positions, constraint forces, accelerations. and we create the meters in advance of running the simulation. And the reason we create them in advance of running the simulation is it helps the simulation run more efficiently. It's not necessarily calculating all the information and outputting it when you don't necessarily need it. So if we click and hold and drag this, we can play back the animation that we have in memory. Okay, nice cycle defined there. Say for example we wanted to plot the displacement of this main actuator right here. We can right click on that and choose Insert Meters. We have different characteristics showing up depending on the type of feature it is we're selecting. We'll go ahead and we'll choose Constraint Force, and we can tell it on to which force we'd like to calculate, either the force on the shaft or the force on shaft 2, equal and opposite reactions. In this case it really doesn't matter, and we can express it in a different chord reference frame. So we could use the chords for the constraint to express it in that coordinate system. We could use the shaft's own coordinate system, or we could use the world coordinate system, which I'll do for this. Okay, so we have a meter there. And how about we create a couple meters, since we'll be looking at the stress on this link. Let's create a couple meters for the forces on this link. So I click on the link and I see the two constraints that are associated with it. I'll right click on this 310 and we'll insert a force meter. The force on link B with respect to world. And then we have another one. We have constraint 24. We'll look at the constraint force on that link with respect to world again. So let's go ahead and run the simulation. This message, by the way, is I checked the part and the properties are correct. I think it's just a numerical discrepancy at the beginning of the simulation. So you can see we get a nice readout of these meters, and we can adjust what we want to show on these meters. It's a lot like the metering in Excel in terms of modifying the legends, the colors. And we can also switch this to a digital readout, which is very nice. And we can show the min-max values of that readout. Okay, and we can do this as the simulation is running. If you'll notice, I can move the model as the simulation and modify the meters. Okay, so as I play this back, you can see the tracer on the meters. Gives us a nice graphical representation of what is taking place. Something else that's very nice too, I mentioned we have those visual aids in here that we can use. And if we take a look at this link right here, and constraint, let me see, link B begin. I'm going to temporarily include that in FEA. The only reason I do that is because it allows me to see everything underneath it, and I can easily select those two chords. So I select the two chords that are on this link that are associated with each of those joints, and then I can choose the vectors option right here, and then I can show applied force vectors. Let me close that. So when I run this simulation, I think what I want to do is I want to increase the size of those vectors so we can see them a little better. Let's choose 1, and maybe we'll tone down the narrowness of them. So there we have those two force vectors. That's a great way to visualize the free body diagram or the free body state of that bracket through the entire range of motion. So you see it's going in more to a tension mode there. Okay, we get into a bending mode. So the real benefit of SimWise is that we'll be able to run and sweep a quasi-static FEA through this entire range of motion and take into consideration all those different load points. Okay, so you saw a minute ago, notice how this link here is sort of the rainbow color representing FEA. All I did was right click on that body and choose Include in FEA. And now this body is set to we're set to take a look at the stress in this body. And something else to note, let me go ahead and just grab everything that's under that link right there. Grab that link. And let me grab the chords too. And we'll choose hide all others. Okay, so there's that link. And you'll notice these force vectors, these graphical vectors showing up on each of the hole faces. SimWise doesn't necessarily know onto which faces the loads for the constraint are being applied. You remember that we created these constraints on this body. Actually, we created them on the other body. I had already finished this one. But I put the constraint right at the center there. And I put it at the center because it's important to get proper load distribution between the two ends or the two ears of the bracket. And this one also is on the center as well. But SimWise doesn't necessarily understand onto which geometric faces the calculated loads are being applied. So what we can do is we can right-click these graphics. Let me do that again. And we can choose this Distribute on Face option. And I don't need to do it, it's already been done. But for example, if I said that the loads from this constraint were to be distributed onto that face, you see what it does. It's going to take the loads calculated and put them on that face. So obviously that's not accurate in this situation, so I'll do it again. Distribute on face, I'll pick that face. And if we want to distribute it onto that second face, because we have symmetry here, I can hold down the, whoops, that's the constraint navigator. I can hold down the control key and I can pick that other face. And now you can see it's applying them equally on those two faces. Okay, so now that we've got that time history of that motion in there, we can move this bracket or this link to any position in the simulation we wish and then simply solve the FEA. So let's go ahead and do that. And if I just do the default, it's going to use the default mesh. And you can see that's solved very quickly. Let's take a look at what the mesh looked like for that. We'll show mesh. So it's a coarse mesh, but it doesn't necessarily mean it is a bad mesh. We simply would want to be sure that we refined it to some degree to make sure we're converging on a good solution for that. The stress is well below the yield strength of the material. And I see some hot spots in there. Red is not always necessarily meaning failure. It just means that that's the highest point of stress in this bracket. So what we would do is let's first take a look at the deformed shape so we can see what that looks like. And we're exaggerating this deformation about 6,400 times the actual size. Let's go ahead and animate that so we can get a nice animation of that. We can also save this as a video if we wanted to. Okay, we'll uncheck the Show Deformed. And so what we might want to do is then, once we've got that basic stress idea, we can use the H-adaptive that we talked about before. So if we click on H-adaptivity, what that's going to do, let me show you the default setting for that real quick. That is going to refine the mesh only in areas of a high stress gradient. Sometimes when mesh elements transition from one to another, they go from a large element to a small element, or they may be distorted. You can have high stress gradients across those elements, meaning you've got a high stress on one element and it's very small on the next. That can introduce error into the FE results. SimWise has the H-adaptive technique where we can specify a certain target error to fall within. And there's some other criteria we can use here, as you can see. I'm going to use the default. Let's try to achieve a stress error less than 10%, and we'll try and do that within 2 iterations. So if I click on the H-adaptive solve button, you can see it solved very quickly in 1 iteration. Okay, and say for example I wanted to refine it even more. It achieved 6.17. How about we choose a target error of 5 and continue? Okay, and it exceeded that. So it achieved 3.87, and you can see how the mesh is getting smaller. So H-adaptive is a great tool for remaining efficient with your FEA results. So it won't necessarily create a nice tight mesh across the entire part when that may not always be necessary. It only focuses on the areas of importance. So let's go ahead and let's double click that part. And if I double click that part to open up this properties dialog, here's the FEA tab. And I can delete the mesh. This is where the initial mesh is specified. So by default, it's using this default mesh size. So if I click on mesh, I can see what that looks like. If I tighten up what we call the mesh factor, I can do it again. And it'll get even smaller. Let's try something like 0.1. So you can see it's a pretty fast mesher. Okay, but what we'll do is just we'll leave the default for this, choose apply, and when we're making these first pass results and getting a basic idea of the stress in our member, it's okay to use a coarser mesh. When we get closer to the final design, that's when we want to start making sure that we've got a good mesh, and from one run to the next we're converging on a good solution. So I'm going to go ahead and change that back to stress, and I'm going to show everything in the model, and I'm going to rewind it. Now what I'm going to do is do a simultaneous motion and FEA solve. This is sort of a quasi-static analysis that we mentioned before. Go ahead and run this. The benefit to this is that it's going to sweep through the entire range of motion, and then I'll be able to create a plot of the stress for that entire range. By default, it creates the von Mises stress plot. So the von Mises criterion is a good failure criterion for ductile materials. Oops, I accidentally stopped it there. And I'm rolling my scroll button, that's why it's stopping. I was trying to zoom out a little bit. And we can do other things like plot the displacements, the strain, the principal stresses, and we can show those on meters. So as soon as this is finished, we'll take a look at that. Okay, I might stop it prematurely. I'm not going to let it run through the entire range of simulation. I was going to run a durability on this, but I'm going to open up another part for that and take a look. So let's just go ahead and stop it. By the way, it may be important to cycle this thing through the entire range of motion, because then we may get a reverse state of loading on it. That could be very critical to a durability or a fatigue analysis. So if I click and drag this slider, basically I've got not only the motion simulation results, but I've also got the stress results. And you can see on the legend here, the stress is changing as I move this back and forth. What I can also do is right click on this and choose Insert Meters, FEA Result. I get a nice von Mises plot of that stress range right there. So you can see how quick that was to be able to perform that. Okay, I'm going to go ahead and rewind this to the beginning. And what I'm going to do is demonstrate what might happen if we want to import a new design, or how we would go about doing that. So we have another link stored that has a cutout or relief already designed in it, and we're going to swap this link out for that redesigned link. So let's go ahead and erase the FEA history. And then what we can do is we can click on that link right there, and you'll notice I may go back and forth. As an experienced user, I'll click things on the screen here, or I'll go over to the browser and click them. It's nice that you have the ability to go back and forth. But there are two constraints associated with this link. I'm going to go ahead and I'm going to select both those constraints, and then I'll right mouse click and split. Basically, I'm disjoining the two chords making up that constraint. Again, one chord belongs to one body, another chord belongs to another body. So I'm separating it so I can associate it with a new body. I'm going to go ahead and read in the new body so I can insert some new geometry here. And I'm going to change it, actually I don't need to. I've got an ASYS file here of the redesign. I'll choose that and open it up. And if the drawing origin has not changed in the CATIA model, that part will fall right into place where it was initially. If it did change its location, I do have the ability, as I mentioned before, when creating constraints, to use sort of that CAD type nature where you can join bodies together and reposition as you need to. Okay, so now I have that new body in the model, and what I need to do is transfer the chords from the old body to the new body. So I pick those two chords, and all I'm going to do is simply click, drag, and drop onto the new body. And now if I look at this link B, it now shows the two split restraints or constraints. I'm going to go ahead and select those two constraints, right click, and join together. So now it's just reassociated those chords excuse me, with the new body. If I click on that link B begin, that was my beginning design, that's why I had it titled that, I don't have anything associated with that anymore except that FEA plot, which I don't need. So I can just select those and press delete. And now you can see we have that link that's joined up, and if I run that motion simulation, it's behaving just perfectly. Okay, and just in the interest of time, I'm not going to run it through the entire simulation, but I could move it, say, to that position right there, and I'll just go ahead and I'll solve. Oh, I need to include that body in FEA, don't I? Okay, and I'm going to refresh the graphics. Okay, here's a good example. So I brought this body in, and the program recognized that the faces that the load entities were assigned to are gone. So I need to reassign those load entity faces. And so what I'll do is I'll just redefine the faces. This one over here is okay. It picked it up automatically. But I can see that the load entities for this joint are being applied to that inside face, and that's not correct. So I'll distribute those onto that face and also that face right there. So now I've got an equal distribution. So now if I solve this, this one's going to take a little bit longer to mesh because now I've got some small fillets in there that it's having to place some elements in. But even so, it's still a pretty quick solve considering the complexity of the geometry. Okay, and there's our final result. So you can see we have a couple hot spots. Again, not necessarily failure, but we won't want to pay attention to this area. It's probably an area that it's being bent. If we show the deformed shape, sure enough, we can see that there's going to be some stress there because of the bending. By the way, we can right-click on this legend and also see the displacement values. So there's a displacement plot, roughly 0.01 millimeters. So as a final design, what I'd want to do if I was sure that that was my maximum or worst case load condition, as I mentioned before, I'd want to use H-adaptive and refine this mesh and make sure that I'm converging on a solution. And by converging, I mean we make successive runs and refinements to the mesh until the point where we see the stress values are not significantly changing from one run to the next. Sort of plateau, if you will. Okay, so I'm going to switch to another example I have here, and we'll take a look at a durability analysis. And I'm going to do this sort of in a different way. I thought this would be good. It would give you sort of a different breadth of using the program. We're going to look at doing a fatigue analysis on this link right here. Okay, so I'm going to go ahead and open up the CATIA file for that and read it in directly. And this is, let's see, where do I have my, actually it's back here. And this is the 3-point front brace. And there we go. Okay, let's turn off the perspective mode. Okay, so the first thing we'll do is begin defining the restraints on this. So I'll pick these inside cylindrical faces. The faces are split into two halves, so I'm going to go ahead and select the other halves here. We'll also apply restraints on these inside faces of these ears because they do in fact butt up against some other components that would prevent that lateral movement. Now that we've defined those, let's change the type of restraint that those are. By default, you can see that those restraints are completely rigid restraints locking all degrees of freedom. That's a bit over restraining for this example. What we want to do is get something that's a little more realistic to its physical condition. So we'll go ahead and we'll grab all of these restraints simultaneously, and we'll change them to be normal to their respective faces. Notice how we also have the ability to use cylindrical coordinates as well in here, where if we do that, it gives us radial, tangential, and z-axis. So different options for restraining these. Next, we'll go ahead and we'll apply the force acting on this eyelet. This is where the actuator connects to this link. So we're assuming we have extracted loads, maybe from physical testing, that we know the load time history that's applied to this particular eyelet hole right here. So we'll click on the structural load tab and we'll click on that face. Okay, and then what we'll do is we'll define what that load's going to be. I'll just double click that icon to open up its properties. Click on the structural load tab and we'll use world as the reference frame, Cartesian coordinate system. And then I'll click on the triple dot button to access the formula builder. And just like we did for the actuator inputs, I'm going to read in test data that I have stored. So I've got the XYZ force data sets for that load history. And you can see it spans an interval of 9 seconds. Next we'll read in the Y values. And then finally the Z values. Okay. Right now it doesn't look like anything because time is actually less than 0, if you will. We haven't started the simulation, so it doesn't know what the force is just yet. So let's go ahead and let's change the material of this. Since I do not have titanium set up as a durability material right now, I'll go ahead and use aluminum. I'll choose 7075 T6. It has durability properties defined for it. Choose OK. And then I'm also going to make a couple modifications to the simulation settings. First, I'm going to define a stop control that stops the simulation after 9 seconds. Because we don't need any more time than that. That was enough to cover our load history. And then next, we'll set the integration or the animation step size to something larger, maybe we'll say 0.4. It can be larger in this case because we've already extracted the load information. So we've got accurate loads. The program will do just will be fine interpolating along that data curve on its own. Okay, so we're ready to run the simulation. In order to solve a fatigue or a durability calculation, we must have time load history in there. So it needs to be force versus time. It cannot be just a static FEA. So we run the motion with FEA, and we'll go ahead and run this. And whoops, one thing I forgot to do was include this body in the FEA. So let's do that and let's run that again. And by default, it's going to use the default mesh like we talked about before. After I make a first pass at this and assess the results, I can always then go back and see if I need to refine the mesh in any spot using H-adaptive methods. And we're almost complete. You can see down here in the bottom right that we're almost at 9 seconds. There we go. So we have 9 seconds of data. So if I look at what that history looks like, okay, and I can also right click on this and I can insert a stress plot for the history of that. And we're looking at pascals. I probably want to change our units to megapascals. There we go. Okay, so there's our load history on this. It's very simple from this point to complete a durability calculation. All we'd need to do is define some durability criteria settings or maybe some factors. So if we look under durability here, we can choose the criterion we wish to use depending on if we've got fully reversed loading, ductile, tensile materials. We also have input factors, or an input here. We don't necessarily need to go through the full 0 to 9 seconds. We could only go for a portion of that, maybe 5 to 6 seconds if we wanted to. And then we have fatigue factors that we can define. And these things will reduce, they introduce what we call notch effects to the fatigue model. And they're going to aid in reducing the life of the fatigue life. So if we choose forged, for example, it puts a factor in there, and that's going to reduce that life. And then we have some iteration control in how we can control the convergence of the durability calculations. So I'll go ahead and just click that little N button right there to run the durability calculation. And there we have our fatigue life results. And what it is, it's worth using some of the different fatigue criteria to just check your results. depending on the type of loading, the type of material that you have, to make sure that you're within a good reasonable range for the fatigue calculations. But just as an example, you can see that we have roughly 1.3 e to the 8th cycles on this. If we were to change the fatigue factors and say that it was a polished part, for example, we can see how that will alter the fatigue life and actually help to increase it. Okay, so that's pretty much all I had for this demonstration. Next time we'll be looking at SimWise as an associative plugin with the CAD system. In that particular case, we'll be using SolidWorks, and we can see how it's really beneficial to have it linked to a CAD program to leverage the associativity and the design change between, or the changes between the design model and the virtual prototype model. So that completes the demonstration that I had, and I'm going to now pass it back to William.
All right, thank you, Scott. This was very informative. I guess one of the talking points that differentiates really SimWise from a lot of the other products is the fact that you are capable of solving for stress as you're calculating the motion. I say the majority of the products out there have you juggle between products, pass loads around, and do mapping of the constraints and all this, and so which is fairly inefficient. And once, as you mentioned before, the max load is not necessarily the max stress. So the only proper way of finding the max stress is to solve for stress across the entire range of motion, which is not necessarily easy if what you're doing is passing loads between two different products. With SimWise, it's done automatically as you're solving. So along with that, being able to deal with CAD geometry from pretty much anything on the market within an embedded product or within simply translators, being neutral format or actual native translators, including in bringing material information from CATIA, for instance, or SolidWorks, is a big bonus that I think would be a great advantage to the SimWise users. We're going to have another webinar to finish up and to brush up on a certain number of other topics next week, so we'll send the invites for that. In the meantime, we'll post this webinar recording on our website. We'll post that on our website, on our YouTube channel. If you want more information, feel free to contact us. Some of the links there to follow, either contact us, look at our product list, or look at examples through our YouTube channel or LinkedIn or Twitter. And we'll be more than happy to address any questions that you have. That's it for now, and hopefully we'll see you next week.